Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right, hello everybody. Finally, a new introduction
He did
to
it.
the live stream.
You have finally done it. You
Finally
made
had the
a
time.
new intro, and it doesn't talk about trade shows from 6 years ago.
Yes.
Although I'm gonna miss that so much.
Yeah, I know. There was kind of like this maybe high energy bang that came with it. But I finally have a little bit of time to work on improving the live stream experience. So man, it's a time coming.
I'm not sure what we're gonna do though, because the beginning now was you reading all the boilerplate stuff, and you just did it in the live stream video.
Yeah.
So now we just get to start.
We can just start. We can just mention any other things, just like reminders. Hey, if you're a tier 1, oh yeah, here we go. Chris has mentioned it. Yes, it's about time. And Chris, I remember I remember Chris making a comment about that some time ago. It's like, yes, it's about time that we have a new introduction. So yes, finally getting around to it. Thank you for noticing, Chris.
That's
always
right.
good to hear from you. We're also we normally stream to YouTube, and now we're finally we're trying to stream on LinkedIn as well. So if you're on LinkedIn, say hello, ask us any questions. We're always happy to try and answer these. So hopefully this will be a recurring thing as I try to improve things.
Yes, and we will be using this intro video from now on. That is not from forever ago.
Yeah,
and we will be streaming on eventually every platform in the known universe, and it will just keep growing and growing, and I'm excited.
Yeah. No, it's very good. So yeah, so type your questions in. We do take, of course, questions that have been asked from previous live streams or YouTube comments, webinars, things like that. Both Neil and I got a question earlier this week from GoCool. And so GoCool, to kind of summarize his question, he asked us these kind of email related questions about this special PLU graphene glassy carbon electrode. And he's not really getting good or any CV or EIS signal compared to the literature value. And I think this would be at least a nice starting off point, something we can at least talk about in the beginning. But I have some of the data that he graciously, I guess, shared with me and Neil. So let's minimize that. So this is some of the data that GoCool shared. He shared some cyclic voltammetry data on the left and some EIS data on the right. And maybe I will, actually, they're all pretty big, but maybe I can make this a little bit bigger. I'll move this over here so everyone can kind of see. So he has a ferricyanide solution here, and I believe the electrochemical system that GoCool is talking about is he has a glassy carbon electrode. He's looking at ferricyanide, and right now he's just trying to understand the electrochemical response by modifying the bare glassy carbon electrode. And so in the cyclic voltammetry, he's getting these kind of normal cyclic voltammograms, normal-ish cyclic voltammograms one would associate with ferricyanide. One thing that's interesting to note is that the current, if he's scanning from negative 0.2 volts to positive 0.6 volts, he's starting actually at a negative current. So he may have either a mixture of ferri and ferricyanide, or he's actually already reducing or oxidizing, depending on his convention, his CV plotting convention. He may already be reducing something at the start of the experiment. This may also describe why we're seeing some crossover also in this voltammogram. But either case, he has this bare, black is just bare glassy carbon. And then he modifies the glassy carbon with some graphene. And then he uses this polymer, an electroactive polymer, that's just called named PLU
I think
or
it's
poly
polyluminol.
polyluminol.
Yeah, I'm not exactly sure anything about it, to be honest.
Yeah, I don't know anything about it either. I'm used to anilines as being kind of the electroactive
Yeah,
polymer.
polyaniline is electroactive
Polyaniline.
for sure.
But I haven't this, but he just calls it plum or PLU for short. And when he makes this graphene PLU mixture, so to say, on the glassy carbon electrode, we can see that he gets no signal in the CV. There's very little to no electrochemical response that we're observing. Now he also says, hey, at the same time, when I do EIS of this system, he kind of zooms in. This is his Nyquist plot, and I think that's orthonormal. And then he also, at least I think it's
Yeah,
orthonormal.
it
It looks orthonormal.
yeah.
He zooms in here because it's usually the case that sometimes all your EIS data is actually contained to a very small part, and all the low frequency stuff is just way out there. But he zooms in on this little region in the Nyquist plot, and he shows that, okay, for the bare glassy carbon electrode and for the graphene modified glassy carbon electrode, he gets these normal Nyquist plots. I think it's hard to see here, but you do get a small semicircle with a diffusional tail, what you would normally expect when looking at ferrocyanide. But in the case of this graphene with plum, I'm just going to call it plum, he doesn't see that. He does not see the semicircle, and you just get this kind of what you may describe as a diffusional tail just going straight up. But I don't know if I'd call it a diffusional tail, especially when we have the CV data to confirm that there's really very little to no current response that's here. Now he's saying, if we move on, he showed this image from the literature. He's just trying to reproduce a literature study, which is very, which is normal, perfectly normal. We all try to do that, especially when we are in graduate school. And he's trying to kind of reproduce these Nyquist plots, or at least get something similar, or should see a similar trend in terms of getting these semicircles and a diffusional tail. And so his real question is, what he's really trying to determine is, why is it the case that he's not getting the blue Nyquist plot? Why is he not getting a small charge transfer resistance and then a diffusional tail? He's getting nothing. He's just getting a straight line. And he has the CV data as well, which he did not share. He didn't show any CV data from the paper. But his question has to do with this. Why is he getting that? Now, when you ask questions like this, and actually this is very interesting. So frequency from 100 megahertz to 100 kilohertz. That's actually very interesting, or very strange. That feels like a typo.
Feels like should be millihertz.
Yeah,
Seems almost nobody. It's not possible to do 100 megahertz.
Yeah,
practically, I don't believe there's an instrument that can go above 10.
Yeah, exactly. This feels like a typo. So I think maybe this also kind of begs the question on some of these things. But in general, this is a kind of very specific kind of question, which we're happy to try to entertain. But usually this comes down to something where we actually don't know what the answer is. There are too many variables involved in this specific electrochemical system. Our own personal experience working with electroactive polymers. But one thing that, because Neil and I have talked with this person, at least via email, about the system, and we want to at least discuss it with him and you, and I think it's an important thing to share, is that you need to make sure that you are reproducing the procedure almost exactly, like to a T, in as the literature has it. And it may also be the case that, when the literature says, like, oh, we did a bunch of things and we got this result, There may be subtle things that they may have omitted or forgot to mention that are important to reproducing that result. It may be a little bit of trial and error. That may have been actually some of the best EIS data that they got for that system, and they went for it to publish it. But it may actually be very difficult to create this graphene polymer film electrode, and the preparation and and how it was created may actually be very different. And so my first impression, at least, when you see no signal at all, is that, well, at least on the CV, is that your film is not actually conductive. It's blocking. It's actually insulating. That's my first impression, just based on looking at a glassy carbon electrode and then glassy carbon with graphene. And then when you add the polymer, I think it's actually insulating. There's something wrong with the polymer because you're not getting any current response for a somewhat well characterized system. So go cool. If you're watching this, this is kind of something that we discussed or looked at, thought about, and these are just, I would just strongly encourage you to try to reproduce, even buying your chemicals from the exact same supplier, even reproduce those types of results, the experiment exactly as it is written. Um, and it may be a little bit of trial and error. You may have to use some other techniques to understand what is happening on the surface of your electrode. You may have to take some images of your electrode, um, do other techniques besides EIS and CV to characterize the electrode surface to really understand what is going on in your system. So hopefully that's helpful. That's also hopefully a lesson for all of you who are, just learning electrochemistry and figuring out what to do.
And I'll say that for like a very brief amount of time that I've mostly blocked out of my memory, when I was in graduate school, I had to try to work with polyaniline.
Mm,
I was doing some little project with like
yeah.
polyaniline, maybe polypyrrole. There's a few polymers that are electrochemically relevant, I guess, or they can
Yeah.
make films, and it was awful.
Yeah.
Like it was awful. And so the idea that your electrode fabrication is the problem is most probably correct, which is to say, you have no signal, like you said.
Yeah.
Something is insulating. Like you're not getting an electrochemical response, which is what my reply to you was. This person, when they emailed me as well, there's something going on, most probably, with the electrode fabrication that you do not like. If you have literature, research, and evidence, that polyluminol is uh, like electrocatalytically active towards ferrocyanide, and people are showing, okay, one of two things is true. One is that very, very small response looked like there were some peaks, but they were really small. If you zoom in on the y-axis, you would like resolve those.
Mhm.
So one of two things is true. One is that it actually is catalyzing the ferrocyanide. You got to zoom in really far, and it's not nearly as electroactive as bare glassy carbon, which is bad.
Yeah.
And so it appears somewhat insulating. It just has really low catalytic activity.
Mhm.
Or it's not polymerized. There's something else on your
Yeah.
film. The ratio of active and binding materials is off. It didn't actually absorb to the film at all. It delaminated.
Mhm.
I don't know, like any of a number of possible problems are occurring such that you have an insulating or a lack of a signal on your surface, and you're just not getting what you want. So very, very generally and gently, I would tell you to investigate your electrode fabrication process, because something
Mhm.
is probably wrong.
Yeah.
And beyond that, we just don't know enough details to know exactly
Yeah.
what you're doing or what might be the problem. But you're definitely getting no signal. So
Yeah. Yeah.
okay, so there's a question here from Digwell, and Chris
Mhm.
is helping kind of clarify a few things as well.
Mhm.
But they say, if we measure the solution resistance by EIS and get resistance is negative, what does it mean?
Mhm.
And so Chris asked, what system is it? They said a coin cell, and then you're talking about a CV curve. So in some sense, CV curve can help get you some context. On a battery with a coin cell, it isn't always quite as necessary, especially in the context of the solution resistance. So there's one of, well, let me put it this way. The first and short answer is that you might have, well, what I would have said before you said coin cell was that you possibly have some kind of a reference artifact kind of a problem going on. So in many times when you are studying systems that give you a sort of odd behavior at high frequency, you get something that looks maybe a little bit like this. So you might have a Nyquist plot and at the highest frequencies all the way on the left here, it starts to veer into negative territory. Or you have like a semicircle that doesn't complete, but if it did, it would complete in negative Z real. See, this is the Z real down here. It's like odd to see. So that might be part of it. Very possibly. I can't know for sure. But sometimes that's the case. Now, when it comes to your situation, I'm going to pull this one here. Let me pull some stuff up because you have a coin cell, and I want to find some other data I have on coin cells, or at least batteries for what it's worth here. This maybe isn't a coin cell, but it's a cylindrical battery. In any case, when you say you did it with EIS, the one of the questions that I have, for instance, is it one of those potentiostats where there's the automatic, it sort of does it for you, kind of like sniff the EIS, you know what I mean? Whatever you want to call it. Or did you do impedance yourself and look at the data and say to yourself, this is what it is? So those are two sort of options, right? If it was a potentiostat and you use the program that's like get IR drop or get solution resistance for me, then one of the things that you need to sort of be aware of is what is the software doing? Okay. So there are two kinds of errors, I suppose, or just odd behaviors that occur at high frequency that can lead to this kind of an error. And this is the other one is what you're looking at right now. So before I showed you where sometimes you have this situation where you have the so-called negative impedance here, right, at the highest frequencies, negative Z real, I suppose. Okay. And then the other is that with a battery, you often get something that looks like this. Okay. And that you have this inductance. This is essentially what this is. So you have a lot of inductance. It comes with the territory with batteries a lot of the times because they have extremely low impedance. You see milliohms on the x-axis down here. And so you have this odd phenomena where at the highest frequencies, you have inductive behavior. And so you have another negative quantity on the y-axis here, not on the x-axis. Okay. Now, strictly speaking, definitionally, what you would want to do to obtain, and I'm talking about kind of in a manual way, the solution resistance or the IR drop, is you would basically take your data, your plot, right? I'm going to zoom in a little here for you. And you're going to find where the Z real is when Zi equals 0. Okay. So when the y-axis is 0 at high frequency, what is the Z real? And so in this case, you can see it'd be about 70 milliohms. That would be my solution resistance. That is like mathematically equivalent to what it is. Now, I'm going to tell you where sometimes the automatic programs can go wrong. And that's because on the Bode plot, let me get one that's a little bit, this one maybe looks a little bit more interesting. Yeah. Okay. So what I just described to you, the Z real where the Zi is 0, that corresponds to a phase angle of 0 degrees. And so what an automatic program will sometimes do, okay, is it will look at the phase angle plot, the blue dots here, and find the phase angle that's closest to 0. So it might be, let me get like a point. So somewhere in this range, right? One of these points is closest to 0. Then its job is to take an impedance value corresponding to that phase angle that's closest, because it doesn't totally get to exactly 0 all the time, maybe, right? Now, the smart way a program would do this is it would take the phase angle closest to 0 and then take the corresponding either Z magnitude or Z real. Now, if the phase angle is 0, Z magnitude equals Z real. But you can just say one of those two will be close. On the other hand, sometimes what happens is you might get a program that just picks a frequency like 100 or 400K, which might be down here. Now you can see you start getting a problem because this is where the inductive or weird behavior might start to occur. Let me go back to the battery one here. This is where we have this inductive behavior. And so you have another odd situation that can occur. If the program picks a high frequency, like here's whatever this is, like a 20,000, 30, 50, 80,000 or 8,000, whatever hertz, you could end up in a similarly odd situation. Now you have a positive phase angle because it's inductive behavior. And if it takes the Z imaginary, it might end up as a negative number. So part of the issue here is that you have some automatic program that just assumes this frequency is where it is, and then which impedance parameter is it taking. You can see two instances I've shown you where that number might happen to be negative. So those are a couple ways where you might end up incidentally with what appears to be a negative solution resistance. Now, fundamentally and practically, this is impossible. It's not. There's no such thing as a negative resistance. Not strictly speaking, it doesn't really make any sense physically. It's like your electrolyte is so conductive, it's generating energy for you. It's like, congratulations on your Nobel Peace Prize. Like that isn't a thing, right? So so those are a couple of possibilities. I think that probably the first one I showed you, which happens because of reference electrode things, you can fix it with a shunt, might not be the case because you're using a coin cell. It's probably a 2-electrode system, so probably has something to do with this inductance. Possibly, like I said, it's picking a frequency, assuming some things, but manually you should try to see if there's a way for you to just get the frequency over a few decades at the higher range and find where Zi is 0 and take the Z real. If it's still negative, then you have a problem. Like something is wrong. Something is malfunctioning either with your instrument or with your cell. It's not. That's not real. It's not like something is inaccurate in some way. And I don't know if I can clarify more on that. It's very unusual that you would see with a coin cell, for instance, something pushing into negative Z real territory. That would be very unusual with a coin cell. I suppose it's not impossible, but it would be unusual. And it probably means that your coin cell, something is fabricated improperly, is my guess. It's for a couple of reasons. It's just not something that probably would be possible. When you need transistors for your circuit fit, something has gone sideways. It sure has.
Yeah,
that's right. Yeah, transistor is one of those odd things, right, where it allows current in one direction, not the other, or whatever. So yeah, not a thing in a EIS. So yeah, Digwell, please follow up if you have any other notes. And also, you did responding to Chris's inquiries as well. You said if I run the CV, where the potential area would be chosen for EISR. So if you're trying to just find the solution resistance, this is why I was saying CV is not necessarily needed, I suppose. You would just do impedance at open circuit to get the solution resistance. It's never going to be this way exactly because nothing works ideally. However, in theory, the solution resistance should be the same regardless of where you are along the state of charge curve. So if you perform at open circuit potential or you're halfway through charging, discharging, you're whatever, for the most part, the electrolyte, it can change. The SEI can decompose it a little. Okay, there's some situations where what I'm saying isn't exactly correct, but for the most part, the electrolyte is largely unchanged. The solution resistance is, in theory, largely unchanged throughout the course of an experiment, even over repetitive cycles. And so while experimentally you'll measure some small changes, for the most part, the answer is it doesn't matter where along the curve. So your best bet is just do OCP, do it at OCV, whatever your open circuit potential is, voltage, whatever, and then do that. And then, try galvanostatic if you're not already. You didn't really specify, but galvanostatic impedance is much more successful on batteries. Typically, it's more stable. And you might have an easier time. Maybe you're doing potentiostatic and it's not going well, and that could be why. Potentiostatic impedance is not usually a good idea on batteries for a variety of reasons.
Very good. Well, Digwell, I hope that was very helpful,
Yes.
which I think he says, I got it. Thank you very much.
Perfect.
Fantastic.
And then actually this next one is pertinent because I was just
Mhm.
doing some stuff on this the other day as well. I can't give you a full answer here, Paul Mining, but I will give you some answer. Hopefully it's pertinent. Explain the mechanism of hydrogen evolution reaction and oxygen evolution reaction in a zinc manganese oxide battery, first of all. And so I don't think you're talking about sort of just HER and OER in general. You're talking about it in the context of a zinc, basically a zinc ion battery, and then how the pH of an electrolyte affects the two reactions. So the second answer is that it does, and I am not prepared really to exactly, for two reasons. One is that I don't know that I know, like off the top of my head, I could find this information. I have in the past, I think on this live stream, there's probably one of the episodes. I'd have to find the right one, as we've done 65 of these or something at this point.
Yeah.
I have gone through the mechanism, I believe, in acidic pH for the oxygen evolution reaction or the oxygen reduction. I can't remember which one. I think it was the oxygen
Yeah.
reduction reaction is like 9,000 steps. Usually, if you read papers,
Yeah, there's a lot of steps.
I think it's the oxygen evolution.
Yeah, like well, I don't know about it in the context of a zinc
right. That's
ion battery. That seems to be the caveat.
right.
But generally speaking, the pH affects the reactions based on the propensity of whether you have like H plus. If you're in an acidic solution, like H plus will be the dominant thing in the mechanism. Or if it's in a very basic condition, you'll have OH minus, and OH minus then plays a role as the thing that either carries the charge or does the, breaks the bond or something like that. And you wouldn't have H plus in the mechanism if your pH is very high.
I mean, all of these reactions, they are technically different when the
pH is different.
Right, when the prevailing, whatever you say, species is hydronium or H plus versus hydroxide.
Correct.
Right, whether you're basic or sorry, I couldn't help it. I had to do the basic comment. So yeah, the mechanism is different. Most of it has to do with the intermediates, and the crap absorbed on the surface at one point or another is proton or it's a hydroxide or whatever it is. So
it's also like pumpkin spice latte time. So the U basic thing is also
basic.
more.
Oh yes, I very much love me a pumpkin spice latte. I am as basic as they come. Basic and proud. Thank you very much. Sorry, I got lost in pumpkin spice latte. Yes. So mechanistically, it's frankly something that I've done. You could probably find it in one of our earlier live streams. Again, not specifically within the context of a zinc ion battery, but I've described the mechanism for the OER in an acid media, for instance. It's like a 4-step process. Every other step, an oxygen is released, and there's an absorption. There's 4 different electrons, and there's 4 steps. As far as a zinc ion battery is concerned, in general, one of the things that I believe is true is that at alkaline pH, the stability of the battery becomes a little more compromised because you get zinc hydroxide, which can flake off. And that's bad. So a lot of times zinc ion batteries, they just use something like zinc sulfate or sodium sulfate, which is probably mildly one or the other, but it's basically neutral for all intents and purposes, right? I mean, it's not a strong acid or base. It's one of those things where
it's not pushing the pH scale.
There's probably, if you look up the pKa, it's probably something, right? So it's probably very like mildly one or the other. Like nothing is really neutral, like per se.
Yeah, that's true.
Technically, right? It's like the relative, like if you have like NaCl, the relative strength of like NaOH versus HCl is slightly different. So the pH is like 6.9 or 7.1, or
just so hard to calculate.
Whatever.
But
so all that is to say is that in one way or another, when you have alkaline stuff, a zinc ion battery can have some trouble. And what I will just basically mention is that the last thing I'll mention here, I suppose two little steps. First is that for the most part, the zinc ion battery consists of a zinc intercalating manganese oxide on one side. This is the cathode. And then on the anode side, you either have basically carbon graphite or zinc metal. Okay. And the general reaction, you can think of it as something like this. Let me see if I write it through properly. Basically, okay, so the cathode, you're going to have manganese dioxide, okay, plus X zinc 2 plus ions. And then because it's a 2 electron process, we'll have 2. Don't ask why. Yeah, that's a Z and that's a 2. And don't ask why this also looks like a Z. It's not zinc Z plus. 2
zinc Z plus.
X electrons because there's a 2 electron process here, right? And so this is, I'll just draw one arrow. This is basically the discharge process for the cathode. Gives you zinc intercalated at some percentage, effectively here manganese dioxide. Okay, and so that's a reduction process. And so this is the cathode. Cathode. That's an A, not a U, not cathode. Okay, and at the anode, you have an oxidation reaction that is something like, let's see if I don't screw this up as well. You have something like X zinc. It's much more simple, I suppose. Gives you X zinc 2 plus ions.
Cross your Z's.
I know, right? Oh, that's a good idea. Thank you. Actually, that's a no, that's a really good idea. Yeah. It actually makes it easier. I sometimes do that, and I actually forgot. You're not wrong. Thank you for that. Yeah, I know you're thinking out loud, but that was exactly what I needed to make this not look ridiculous. Okay. Anyway, the zinc. So basically, at the anode, zinc metal during discharge is oxidized into zinc ions. They travel across to the cathode where they're intercalated. That's how it discharges. And then the charging process is just the opposite. Okay, so that's basically like, this isn't exactly oxygen evolution, hydrogen evolution. Those are things that do happen also. But that's sort of the overall zinc ion battery chemistry, if you will. The second part of this answer is that what I just showed you is a lie. I just lied to you. I literally lied to you. So I'm very, very sorry. I had to lie to you for a reason, to protect your innocence. And the reason is that I will just show you this very briefly, and I'm not going to dwell on it too much, but this is a really good paper. This is a chemical review from, I think, 3 or 4 years ago. You can see, this is what I talked about, for example, there's a dissolution process that happens with zinc hydroxide. So when you have really high pH, you get all this crap. It's bad. Zinc starts to dissolve. It's terrible. And it makes dendrites, which is another battery related problem. But mechanistically, zinc ion batteries have a lot of, so there's some manganese oxidation and stuff, but mainly there's a lot of stuff that happens. All right. And so this is one, for example, there's this manganese makes oxyhydroxide, and you end up with this like zinc sulfate, zinc hydroxide amalgamation of some sort. That's one that happens with a particular type of conversion of manganese oxide with zinc. This is the reaction that I just actually showed you. So it looks like I got it mostly right, I think. They don't cross their Z's, so they're wrong. Okay, and then there's other possibilities here. This is a similar kind of a thing here. Zinc sulfate with a different proportion of zinc hydroxide. You have a different, I don't know, valence of manganese oxide, maybe a spinel or some other kind of thing that can occur. And one of the reasons for this, basically, which is why I just acknowledged I lied to you, is that zinc, strictly speaking, that's not the one. That's Z204. ZnMnO2, like what I drew for you, actually doesn't physically happen. Like spectroscopic analyses have shown that that's not actually what occurs. It's just like the most basic, dumbed down, electrochemistry, like that is effectively happening, but there's other complex structures that are really forming something. I don't know how better to kind of simplify it than that, but basically that's, you can simplify it as in this way, and mechanistically it's quite complicated. And as you can even see that I'll put this DOI of this paper in the chat for you. It describes some of these kinds of mechanisms. I don't know if specifically HER and OER are in here. They might be. This is quite comprehensive review. It's a very, very good paper to give some accreditation here to the authors you can see on the screen right now. I don't know where they're located. In any case, I'll copy the DOI I just wanted to give credit where it is due, of course. And so that's what I can tell you about zinc ion battery review paper. So I don't know if that's going into LinkedIn. You might want to put it there just in case. I don't know if it went to LinkedIn because
that's a good idea.
Because it was Restream was just telling me this might not go to all platforms. It went to YouTube, but it might not go to there. So, Chris said to cross my Z's. Yeah, thanks.
Chris. Chris said
see, I
just did whatever.
See, Alex is taking credit. I didn't even know that it was Chris's idea. So thank you, Chris.
It was Chris's idea.
Yeah, you made the Z's a lot better.
I just read what
you read what Chris did, and you just
Chris did. I just said it.
Took all his credit. He was the one giving the good advice.
I didn't even know I was giving credit to people.
That's right. All right, we're stealing all of Chris's ideas from now on.
Let's see. The next question we have is from Satish. He says, I have EIS data for a full pouch cell. Will you please suggest the fitting model for it?
You really need to see your data to know that.
Because depending on how many semicircles they have, you could have a variety of different things happening. So
you'll have to send us data one way or another, Satish. You'll have to email it to us. You could join us on the live stream as we've talked about here.
Yeah. If you're a tier 1, tier 2 member, you can join us.
We need to see the data because it really I can't. I mean, I could give you a million different possible.
It's not like a Randles circuit for like an like just a 3 electrode system with a redox couple. It could be a bunch of different.
Be a million different things. You could have Warburg. You could not have Warburg. So we would need to see the data, and then I could suggest a bunch of models that might work. If you gave me the data in like CSV form, I could even fit it for you right now, live.
Wow!
Can you imagine that?
That's pretty crazy.
But I would need your data. I don't have it. I can't do anything. All I have are words, and I simply cannot do very much. So contact us further. If there's a way for you to get it to us within the next 1 hour and 20 minutes or so, we can try to look at it. If that happens. Otherwise, maybe for next week or something.
This could absolutely be
we're happy to help
kind of thing.
Do fitting. I really like helping people with their circuit fits. I do that pretty often. So get us the data. I'll see what I can do.
All right. Next question is from Joel Johnny. What is the proper way to electrochemically activate electrodes for water splitting?
This is good. You talked about this the other day.
Yeah. So I talked a little bit about just what it means to quote activate your electrode. And when I'm saying activate, usually people will activate things like a glassy carbon electrode or something, maybe a pure platinum or a nickel electrode or something. But generally speaking, the way to do this is to do electrochemical cycling, sort of say. So I will share my screen just so that people can kind of see. So if we just do a new slide, I delete these things. Let's go to review. So if you have a cyclic voltammogram, or if you're in like a 3 electrode setup and you're trying to clean your electrode, you have your voltage here, you've got your current here, and what you want to do is you would like to cycle the potential. Let's say you start here. This is where you're starting. You want to cycle, you want to sweep such that you're oxidizing some stuff off of the surface. So you pick a potential. You're not trying to drive a ton of current here. You don't want other processes or possibly the electrode to degrade. But you want to drive a considerable amount of current here, reasonable amount. And then you want to switch it back. And maybe you'll see a little bit of this. I sometimes see this too, a little bit of reduction of whatever oxidized things you have at this potential. You want to sweep it. And then here, you want to reduce stuff on the electrode. So once you find like this kind of general range, sort of say, you just want to cycle the voltage between these potentials many times. You may do it 50 times. You may even do it 100 times. And maybe you pick, I'm going to write a better X there. Okay. You may do it, even more. And generally, sometimes what you'll observe is the first cycle, you'll see these like little bumps, like little tiny like features or whatever on your voltammogram. But as you continue to cycle, those features will go away. They'll slowly start to disappear. You'll get less and less of them over as you start to cycle the electrode. And the voltammograms will literally just overlap one on top of each other. And that is a way of preparing the electrode such that you've oxidized any junk or contaminants that might be on the surface that's blocking an active site, and then reducing, again, contaminants. You mostly want to deal with the oxidation. Oxidation is usually the way to go, but sometimes you still may want to, you need to reduce something off the surface. So that in general is the way you want to electrochemically activate your electrode for any kind of reaction. I think, and specifically you were talking about water splitting. Of course, every electrochemical system is a little different. So you might want to be careful, because if you have like a thin film, you may oxidize off the thin film. Or you may do anodic stripping voltammetry by accident, and you get like a huge wave or something, and then the next one, like, you see nothing, and it's like, oh, I actually wanted this. I just got rid of the catalytic material on my surface that I'm trying to use for water splitting. So sometimes you can or you can't do that. And each system will be a little bit different depending on what kind of electrochemical system you're preparing, because some thin films are very sensitive. But hey, if you just have like an alloyed nickel or something and it's pretty stable, you can do this and create a reproducible, clean surface for hydrogen evolution. So that's the general answer, I would say, for electrochemically activating your electrodes. Okay, and of course, if you have any questions, please follow up with us. Let's see, we are getting a few more questions coming in. We have one from Satan. Satan Adak is asking, can we say EIS is a Fourier transform of CV? No, I don't think you can.
No,
It's just not a Fourier transform of CV. So I like the idea, or the thought of it, as a way of perhaps deconstructing the relationship between EIS and CV. But in a way, Fourier transforms are used in EIS to actually generate the EIS data. Fourier transforms are used, but in CV, I think one thing I would describe with Fourier transforms, traditionally, the way I've experienced them, is Fourier transforms help you take one space and then convert it mathematically into the inverse space. And so, for example, if you are moving something, in say Fourier transformed infrared spectroscopy, you are moving a series of mirrors around as you're collecting IR signal, and then you invert the distance, sort of say. So now you have wave numbers as the units. The Fourier transform converts your distance to inverse distance. When you have, at least in EIS and spectroscopy, you're going from time to inverse time. You're going from seconds to hertz. When you do a Fourier transform to, say, time data, that's probably one of the easiest things. So specifically, we're not taking a Fourier transform of a cyclic voltammogram. We are applying a linear sweep voltammetry. So we're sweeping the potential linearly with time in a CV. We're not kind of inverting that process or inverting the potential in that case, because 1 over potential is not impedance per se. So there are many reasons why, like, the answer is no, we can't.
I think the parallel, or the analog, if you will,
Yeah.
would be to just say the answer is no, as you said. discrepancy, if you will, is that impedance data is calculated by doing a discrete or fast Fourier transform to potential versus time data, but not CV. So to be clear, Fourier transform on potential time data does give you impedance data, but not cyclic voltammetry potential versus time data, right? It's sinusoidal, and as Chris pointed out, the dV/dt is different, which is to say the scan rate is different. It's not constant. CV has a constant scan rate. Right. An impedance signal is a sinusoidal perturbation, which means it technically has a constantly changing scan rate. And it's frankly span of potential is much more narrow than CV. So for all those reasons, it's not the same exactly.
And it is interesting that like you could, and in ways you've also taught people, like, over in a CV, you can think about doing EIS within small areas of the CV to kind of get data. So I can understand why you might think, oh, like EIS is kind of an extrapolation or taking something
from CV.
And there's information from both of them that are related to each other. But
it's a fundamentally different waveform and technique there. So I hope that kind of clarifies that for you. I want to get to Costas. Had a couple of questions. I think it was related to when you were doing stuff on activation. So he first asked, what scan rate you suggest for this? So for an activation, I mean, it's kind of 100 millivolts per second, 200 mil. Like
you can do it. You can do it fast. You can do it slow. Sometimes slower. It's at a potential for a little bit longer.
Which could be good or bad. It
could be good
depends.
or bad, depending on
which is also related to a second question, which is to say, do you think that if there's a sacrificial agent in the electrolyte, it might be consumed during this process? Maybe. Because just as Alex said, you're sort of doing this wide potential window, and you're wiping junk off of or whatever it might be. A side effect of that could be potentially something unwanted happening. If you have the electrode gets damaged or something, you have to be careful about your limits. Or I don't know, if you have something in the electrolyte could get,
So usually a sacrificial agent is added to make sure that reactions on your counter electrode are able to occur. So if you're doing something on the CV and you need to apply a strong negative potential to reduce something, or let's say oxidize, you most likely want to oxidize something off the working electrode. Well, the counter electrode is going to apply a large negative potential. It's going to do a reduction reaction. You might need to use a sacrificial agent to reduce something on the counter electrode. So there is a good chance it will get consumed.
And then
my guess.
The follow up to that, follow up, because Chris is also giving some answers. Appreciate it, Chris. Similar absolutely. That you might need to do some specific testing to your system. But Costas then asked, so would you suggest replacing the electrolyte? So in the case that you did have what Alex just described as a sacrificial component to your electrolyte for the counter electrode's sake, to facilitate a reduction or whatever, then it might be that you would want to have one electrolyte prepared for the activation process, and then replace and refresh the electrolyte for the proper test itself, whatever you're doing. That might be something that would be a good idea. So I didn't want to skip anybody in line.
That's related true. It's just like I was related to the activation. Okay.
So let's back up here. I think there was NVS Pranit has the next question. I think, does the value of the CPE, the constant phase element, or capacitance in the equivalent circuit for a nanoparticle modified surface indicate the strength of double layer or the charge accumulation on the nanoparticle? It depends on which one you're fitting. So let's just say, for example, you have a very typical kind of analog circuit, which is like a leading resistor, a Randles element, and a Warburg element. Most commonly, the CPE or the capacitor in that case corresponds to the double layer. So it's the capacitance of the double layer is what it very loosely I shouldn't say that. It's pretty specifically, but you know,
Yeah.
there could be other, I don't know, other non-Faradaic or capacitive stuff going on. Maybe that depends on your system. It depends on a million factors, right? But let's just say more very broadly speaking, when you have like one Randles element or something like that, the capacitor represents the double layer strength, the double layer capacitance. You know, these are all somewhat of the same thing. When you say the charge accumulation on the nanoparticle, um, that sounds kind of like the same thing.
Yeah.
You know, I don't
Just do
know.
some math to go from one to the other.
Yeah, like you know what? I don't know what the difference would be, sort of, uh, either physically or even from an explanation perspective,
Mhm.
between a polarized electrode, right, that
Mhm.
has an inner Helmholtz plane with a capacitive layer on it, you know,
Mhm. Yeah.
and distinct from that is some kind of charge accumulation. That's what a capacitor is.
Yeah.
So in my mind, you're kind of describing the same thing, just in slightly different ways. And so it seems
Mhm.
like the answer is both, kind of,
Yeah,
right?
yeah.
I mean, do you see it differently? I don't.
So one thing I would mention about your question is that you have a surface and you've modified it with nanoparticles. So there's a chance that you still have some surface exposed to electrolyte.
Mm,
So the value of your CPE, again, as Neil said, it's going to depend on your modeling and your circuit fitting a little bit, your Nyquist data, because you may have double layer strength or capacitance associated with just the bare electrode. Like if you have a 200 nanometer nanoparticle that's in the realm, or a 500 nanometer particle, let's say it's a sphere. If it's a sphere, actually, why am I using my hands like this? Let me. I have tools. I
it's
can
way
draw.
better to
I
watch you
can draw
draw
my ideas
into
on
the
paper.
ether.
Or yeah. So the way I'm thinking about this is if I have my electrode, whatever. Okay, and then I have a nanoparticle, right? I have nanoparticles here. So what you can see is that, okay, the nanoparticles are here. They're all like touching the surface, and there can be 500 nanometers or something. Well, there's still some area, like let's make this blue here. So there's some area here. There's some solution, right? This isn't like a pinhole free kind of thing, right? So, but these nanoparticles are conductive. So there is some double layer strength. Actually, I'll use slightly thinner. Like there's double layer here in this region. There's also double layer on the nanoparticle because that's also what we observe. So you will, depending again, it depends on the nanoparticles, how they're on the surface. You may see two, and I mean, I'm kind of making this up, but like I think you may see two semicircles. No, they wouldn't look exactly. They might not look exactly like that. They may have actually a considerable amount of overlap on each other. You may actually see two semicircles that represent, like, if this is a big capacitance versus a smaller capacitance, then these will be a little bit more distinct. Charge transfer resistance may be the same, or solution resistance may be the same. Actually, charge transfer resistance might be different with these nanoparticles versus reactions that could be happening here. Again, I'm extrapolating a lot, but you have you could have, your CPE value could have influence from these areas, charge that's built up here.
So they say they saw only one.
They saw only one.
Yep.
Okay, so that could mean several things. I would maybe take an SEM image or something just to confirm, like, you don't have any like pinholes or something like that, or it's all this one thing, because that could also mean that one thing dominates the signal, right? I think, Neil, you've even done this with, like, in aftermath. We can, if you can have two capacitors and they may have very very similar values, um, and it looks like one giant semicircle, and really you only have the data for one giant semicircle. but there could be a factor, the
With-
capacitance of this.
With Randles elements or just capacitors by themselves? With two Randles elements?
If I have two Randles elements or two Voigt elements,
Right.
technically,
Yeah, it's Voigt elements.
you can, if the capacitance of both of those are the same or similar, it will show up as one semicircle.
Yeah, I can show that.
So this is just a thing. I'll stop sharing, but this is just a thing to think about with regard to this kind of like system.
Yeah.
And I agree with what Neil mentioned, which is that the strength of the double layer and the charge accumulation are kind of the same thing.
That's just kind of saying the same thing different ways.
Yeah. So that's just the same thing. So that's the only thing I'd add to that, and how you think about that. And he had a comment. Okay, he only saw one. Let's see. Should we also activate our nanoparticle? Everyone wants to activate everything.
I guess so.
Yeah, activate.
I think there's a danger of this possibly if you have if you have a nanoparticle on FTO. I think it's possible. It depends because to my knowledge and somewhat minimal, I'd say, experience, getting stuff on FTO is sometimes tricky. Maybe it doesn't, the adhesion is tough sometimes for a variety of reasons. It's possible that like aggressively cycling it to some crazy limits could cause it to delaminate or desorb or whatever. So, I mean, if you're not seeing a lot of, I would look in the literature and see, are there a lot of people that make, ITO or FTO substrate electrodes and they do an activation process, then maybe it's safe. I'm not so sure that that's done that frequently, to be honest with you. It might be, and I'm just not aware of it, but I don't know that that's something as frequently done. This whole activation discussion is kind of fascinating because I do think it is something that can be useful in some situations, but it's not necessary in all cases. There are definitely plenty of situations for a lot of typical kinds of electrochemical studies where you can make a film or produce a catalyst, produce an electrode and test it as is. This activation, procedure, I suppose, is not really like absolutely necessary in every situation. Let's just say, find the cases or the literature or the situations where it does seem to be people are, extolling its virtues, I suppose. But otherwise, don't jump to the conclusion that you need to do this on all of yours.
Yeah.
You might end up doing something you regret, like you might end up over oxidizing, over reducing your substrate, the catalyst itself. You might end up causing more harm than good. So just be careful. That's all I kind of say about that.
Yeah, that's true.
Okay. I think Sana
physicist.
How to get sustainable electrodes for water splitting using nickel foam and is that metal organic frameworks?
I think so. Yeah, MOFs.
Sustainable electrode. Are you talking about like sustainable as in from one test to the other they're working, or do you mean sustainable like they're not going to destroy the planet by mining for nickel in the depths of the Earth's core and then it collapses in on itself and we have a sci-fi movie? Those are two different kinds of sustainable. I just want to know what we're talking about.
That's right. So let us know which one.
Which is sustainable. Honestly, either way, I'm not sure I know the answer. I don't know how to keep the Earth from collapsing in on itself. I wish it did. I don't. So that's a problem. But also, foam. So I know some, colleagues or whatnot who do metal organic frameworks. I have no experience with them. I don't really know much about practically like working with metal organic frameworks or anything like that. I worked with nickel when I was in graduate school, but not foam. Foam electrodes are tricky because you often have to find a way to create a rigidity to it to be able to test. So again, I'm sort of operating under the principle of some sustainable, like physical way of making it for electrochemical testing. Foam electrodes are just hard because you have to use like a eutectic or a copper or carbon felt or tape or a platinum wire. You have to connect to it somehow in a way that creates electrical contact, right? And you have to find a way to get the foam immersed in solution or whatever, while avoiding as much as possible the thing that I just said, the connective, material, because if you like use let's say you wrap the metal nickel foam around platinum wire to make connectivity or conductivity or whatever. Well, now the platinum wire is part of your electrode, and the platinum might be just giving you all the best water splitting reaction, and it's not the nickel foam. Like you have to take that into account. Like, is the substrate contributing or not? So practically speaking, I don't have a lot more knowledge of it other than to say that when you work with a mesh or a foam, you just got to find ways of getting your substrate connected and insulated as best as possible using Teflon tape or keeping it on the backside, not immersed in solution, something of that nature. It's a little tricky.
And I don't know enough about MOFs. That's all like synthetic chemistry, making those and making like an iron MOF, something that's, that people can like do chemistry with, but like uses, we have a lot of iron, so we can make a ton of these things or something. But yeah, I don't know. So Sana, hope that was helpful. Let us know if you have any questions or further clarification about.
If you want to clarify about sustaining the Earth in the imminent core collapse from mining nickel from the Earth's core.
Yes,
it's a very common concern of mine. And if you have suggestions, I very much appreciate it.
Nice. Let's see. Going to next, we have another one from Stan Adak. From EIS, we can get diffusion coefficient, electrolyte resistance, capacitance, etc. But what else we can do from EIS? What can we get from EIS?
Well, there's a few other metrics. So like a Garrisher element allows you to calculate a heterogeneous rate constant of a chemical process coupled with an electrochemical process. Other metrics, for example, you can get from a constant phase element, you can get a sort of engineering determination of how non-ideal your system is behaving, in addition to a capacitive measurement. There's probably a few other metrics that I'm not thinking about. The diffusion layer thickness, for instance, comes from Warburg in addition to the diffusion coefficient. And then really the other kind of metric or kind of thing you get from it are second order, I would say, which is to say like how those things, diffusion coefficient, well, maybe not diffusion coefficient, but resistance, capacitance, how those things change over, pick your variable, time, voltage, aging, whatever. Like that's often what impedance is quite most commonly used and most powerful for is in a comparative way. So well, great, I get the resistance or I get the capacitance, but really it's like I have material A and material B, or I have electrolyte A, electrolyte B, or I have time 0 and time 3 weeks. How does the resistance change? Does it get better? Does it get worse? Does that mean it's degrading or not? Impedance is a very useful tool to investigate those kinds of things and how those change over time. I mean, that's basically just the essence of science, is studying how things change. And impedance is a really powerful technique in quantifying and correlating observed changes electrochemically with some metric of it. Well, this is the charge transfer resistance. It went up by 3-fold, and that means the kinetics got slower and my catalyst is behaving more poorly. And this one didn't break down over 3 months, and that means it's doing a lot better. And this is a better for state of the art. And so we should put this in all of our phone batteries. Like those are the kind of answers I'm majorly extrapolating, but that's the sort of thing that you want to try to get from impedance as far as those metrics are concerned. So,
yeah. And, it's also, generally speaking, under, I think, most circumstances, a non-invasive technique. Like you're usually applying such a small perturbation that, in CV, like you could do anodic stripping accidentally during CV, and like you're ripping the molecules off the surface by accident. But EIS usually applies such a small perturbation. The reason you can track those things, what's the lifetime of something over time, so that's also like non-invasive. It didn't change the system so much that it's a completely different system. And I've always found the circuit modeling to be very helpful in helping us get a better understanding of like, oh, I thought this system looked like this, but really the EIS tells me like, oh, I have I think I have gaps in my thin film. You know, I don't have to hook it up to an SEM or another microscope to try to see those. Like you can observe them in another way with the EIS. So you can do a lot of stuff from EIS, which I've come to appreciate over the years. Let's see. We have a question from Ankush Sharma. He asks, calculation of mass from Randles-Sevcik equation, basics, and some discussion. Yeah, I think we can spend a little bit of time.
Do you have that one in your handy equations of your?
I do have the Randles-Sevcik equation. So this is the Randles-Sevcik equation. Let me make this a bit smaller. There are two forms I wrote here. One here is at any temperature, this top one, so maybe a little hard to read. But at room temperature, this one's, I think, a little bit easier to kind of look at. The Randles-Sevcik equation states that in a cyclic voltammogram, the peak current for the species that you're kind of oxidizing or reducing for the first time, that current is equal to 2.69 times 10 to the fifth times the number of electrons transferred raised to the 3/2 power, the area of the electrode, the concentration of the species, the scan rate to the 1/2, and the diffusion coefficient to the 1/2. And below are a list of all the different what each variable is. And if you're doing it at a temperature other than room temperature, you need to include things like the temperature, universal gas constant, some stuff like that. But generally speaking, you're looking at these things. So to kind of answer questions about like the mass per se, I think maybe there's some information you can get from, say, the concentration. Like some people have used the Randles-Sevcik equation if they know the diffusion coefficient and they know the area, the number of electrons transferred. They can adjust the scan rate and they can calculate the concentration, and perhaps you can take the concentration, think about the volume, sort of say, of what you're looking at, or the diffusion layer thickness, sort of say, extrapolate the volume from it. You can get the moles that were generated during that peak, at that peak current, and then maybe you can get some kind of mass from that, some number of moles. But generally speaking, the Randles-Sevcik equation, and I don't know if you want to talk or provide a little bit more about this, Ankush, about specifically what you're like when it comes to the mass. I don't know.
Yeah, that's not really a common
thing.
Extraction from Randles-Sevcik. I mean,
Yeah, you really can't get the mass.
I mean, it's like a secondary and highly assumed thing. You do like a cyclic voltammogram, and from the peak, if you know everything else, you can have to use density, assuming bulk concentration, and somehow extract out grams or something. But it's like, what is that the mass of your electrolyte or like the diffusion layer?
Yeah.
So yeah, I think to a very large degree, this isn't with respect, it's not exactly the right question. You're not really meant to calculate mass from Randles-Sevcik equation. That's not really the correct utilization of that equation.
Yeah. And if you're doing something like, because I know there's a lot of people in doing organic electrosynthesis, and so you're mostly familiar with doing cyclic voltammetry and bulk electrolysis. You need, like, Randles-Sevcik will not tell you anything really about the mass. You need to do the bulk electrolysis, collect the current over time, figure out the charge that was passed, and then use Faraday's constant, assuming you know the number of electrons transferred, use Faraday's constant to convert the coulombs to moles, and then from there you have like the mass, sort of say. But that's for bulk electrolysis. Not Randles-Sevcik. Randles-Sevcik is actually only for even a very specific situation. So if your CV looks kind of like this,
does it have to be reversible?
Well, it doesn't actually have to be reversible. But if you start your voltammogram here, and then you go like this, and then you have this, Randles-Sevcik is really just for here.
Right.
It does not apply to this curve here, to this peak. And you even have to do things like subtract the background current from this.
Yeah.
So you may have to even do like a little bit more of like a linear extrapolation of like what your current is. So this peak current, so this is, I guess, a little bit more detail about Randles-Sevcik. This is what you need to do when you're getting the peak current to use for Randles-Sevcik like analysis, sort of say. So those are that's kind of the depth and important things that you need to keep in mind. So let us know if you have any further questions, Ankush, about that.
Okay, let's see.
Moving forward.
I think another question from Sutan. From which equation we can say theoretically a material is ionically conducting but electrically insulating? I'm not sure is ionically conducting but electrically insulating. So like a membrane.
Oh yeah,
Right.
yeah, like a membrane.
A membrane
That's right.
Electrically insulates, two sides of a fuel cell or a battery, but
Yeah.
it's ionically conducting because ions go through. This is actually a really tough thing, especially in the world of electrochemistry, because very often when it comes to conductivity, I find there to be a lot of trickiness in terminology and confusion with units and measurements, like almost the whole thing when it comes to conductivity. Because when people are talking about conductivity, a lot of times they're talking about ionic conductivity, not electrical conductivity. As far as I know, there is no easy way to maybe impedance in some manner of thinking, but basically, as far as it is as I'm aware, there isn't really an easy equation or calculation for electrical conductivity, so to speak. Maybe the inverse of resistance is kind of conduct. It's like technically unit wise, like resistance is in ohms, and the inverse of ohms is Siemens, and Siemens is a unit of conductivity. So that's kind of an answer, but I don't know that it's something like take the impedance of your system and then just take the inverse of impedance, and that's the conductivity of your system. Like impedance at what frequency, at what, where? It's like there's all sorts of impedance. It changes, right? So it's like that isn't a simple answer necessarily. There's not like one impedance for a system. It depends on the frequency and other factors. Most commonly, the equation that people use is L over RA. So, for instance, for a ionic conductivity of like a membrane, you do like a 4-point probe technique. You have a surface area exposed, you have a distance between the two electrodes, and then that's L. A is the surface area, and you get a measure of the resistance either through impedance or like a very slow like linear sweep voltammetry. You use Ohm's law and you get the resistance, and then it's like you get a resistance and you get a length unit in there, and you get like, what's a Siemens centimeters or Siemens per centimeter, L over RA. So it's Siemens per centimeter. And that's ionic conductivity. But again, it's quite tricky in the field of electrochemistry, I would say, because most of the time I think people are looking for ionic conductivity, but sometimes people are thinking about electrical conductivity in terms of electrolyte strength. And as far as measurement is concerned of that, it's like, it's not clear to me if or how you want to use electrochemistry to measure that. Usually we just talk about the concentration and molarity or something like that. So, so I don't have a direct answer as far as like, there's one equation for one and one equation for the other. Hopefully what I described is some overview for you, but other than that, it is a bit of a tricky thing for me, to be perfectly honest. Yeah. Conductance versus conductivity. Those always, resistance and resistivity. Yeah. These ones always throw me for a loop for a variety of reasons. It's I know there's differences there, but very often we're just talking about conductivity in terms of ionic conductivity. And then every so often you get into the realm of electrical conductivity, and it throws a monkey wrench into the whole problem, as far as I can tell.
God.
So
that's
annoying.
Yeah. God.
I think, all right.
So we have a question from Iesh. When using a 3-electrode system
in California,
hopefully it's chronoamperometry.
Yeah, that's right. You can only do this in California or Canada.
I don't know. Yeah, that's right. Canada. Yeah,
Canada,
it,
CA
it depends
usually.
if you have a if it is in the country
Yeah.
spot or the state spot. Um, is there a reason why the baseline signal is different when measured in solution versus in hydrogel, even though both are made of similar buffer solutions? So that is interesting. The only thing I think, if literally that's the only difference, is that the diffusion coefficient will be different. So I'm gonna try something. I don't
Would
know.
it just be the double layer strength? Because the diffusion coefficient difference wouldn't that, like, based on the Cottrell equation, would
Yeah.
affect how, like, long it takes to get to the baseline if it's diffusion coefficient?
Yes.
So the baseline itself, though, being bigger is like the equivalent of scanning faster. You get like more double layer. So would it have to do with a thicker double layer or not?
There shouldn't. The double layer should only quote manifest itself um, at the very beginning
Uh,
of the experiment because you're just applying a
you're charging it
potential
up or whatever, right? Yeah.
and like you charge it and then like you just hold it and it's
Mhm.
at this level. So double layer charging does happen. So I'm gonna
Doing bulk
try
electrolysis
something.
here. Yeah.
I'm gonna do bulk electron. I'm gonna simulate this. If you don't know, this is our simulation software.
Yeah. We're gonna try to get the
I'm gonna
answer.
try to get the answer to this. So this is now. So yeah. So we'll do this reduction reaction. So we're getting microamps of current. This is going to be just just very regular. Now I'm going to change the diffusion coefficient. So let's say if I'm in my hydrogel, let's say I'm much very
Slower.
slow. So if I simulate that, I get this. So now if I archive these two guys,
Yeah.
I'm going to create a new plot. I'm going to take my normal one. Going to do this. Going to take my slow diffusion coefficient. Oops. I'm going to take this one. I'm going to copy these points. I'm going to put it here. So in this, the baseline is different, especially after the first few seconds.
I
It's
guess
also
maybe
the case
after
that
a while it might end up being roughly the same, but it isn't for a while. So maybe it
yeah,
appears the baseline's different um over unless you wait long enough, something like that,
yeah.
right?
So it slowly, they very slowly kind of get closer together.
Yeah, as you get to
It,
time is infinity,
yeah,
they
yeah,
both technically go to zero, but
yeah.
yeah,
But
so maybe it's just a dramatic difference in diffusion coefficients because a hydrogel is going to have a
that
really slow diffusion.
that's my guess. My
Yeah,
thought is because the diffusion coefficient
I think that's probably
is
the
very
answer.
different. That's why you see like a baseline difference.
And the
Is
thing
my
is that
guess.
both will eventually go to zero in theory, like like at
Yeah,
forever time.
yeah,
But if you're comparing both at the same time stamp,
yeah,
the slower diffusion coefficient is always going to have less current.
yeah, yeah. It's just gonna have
Did I
less
say that
current.
right way? I said that the right way. Yeah,
Yeah,
because it's
yeah, yeah,
slower. So yeah.
yeah. It's slower.
So it dies quicker or whatever. It's like
Yeah, it takes longer for the molecule to get
right.
towards the electrodes. So
So the
that's my
current, so it
thought.
looks like the baseline is different, and it's just at any particular time, one of them has decayed more because of the difference in diffusion.
Yeah, I did a three order of magnitude difference, so it might be different. And
I
this is
would guess
fast
that's
electron transfer
pretty
kinetics.
dramatically different. I don't know if it's 3 orders of magnitude, but
Yeah,
hydrogels
hydrogels.
are certainly not going to be as diffusionally, whatever you'd say, like facile
Yeah,
as a liquid
that's a
system
liquid
where
system.
it's very easy to
Very
get
easy.
stuff
Yeah.
moving, right? So
Yeah, so if you want to, you can play around with this software called Aftermath Live, and you can actually determine. You can see, Ish. You can just play with different diffusion coefficients and see how does the chronoamp, in this case, bulk electrolysis, change
you could load your
when you
data in
change
and
it.
try to match it,
Yeah, you can
you
also
know,
load your data and try to match it,
you
that
know,
kind of thing.
figure
So
almost like iterate on what the diffusion coefficient might be for your system, for instance.
yeah, yeah, that could be a thing.
Mm.
Okay, all right. Moving on. We answered Costa's questions
Mhm.
about sacrificial agents and electrolyte.
Kundan, I think.
Kundan has a question. Could you please tell me when I used silver nitrate for organic solution, how many times I can use reference electrode, or how many times can I use the reference electrode?
The silver nitrate.
Yes. Yeah. So let's see. Also,
Yeah, Chris helped answer too. He's just basically testing it separately. Like usually what you have is some kind of like a master situation that just stays independent from
mhm,
your experiments. You can always test everything against that.
yeah.
So, yeah, there isn't a straight answer to that question because you never really know unless you test it against something else.
Yeah, so it's not going to be, so the reference electrode quality won't be based on how many times you use it, but mostly how long it's being used in an experiment where the concentration of your species inside the reference electrode is changing. And because reference electrodes kind of necessarily leak into and out of the test solution, that concentration is going to change, so the potential is going to change. So uh, you may have to you may only be able to use the electrode like one time because you did a super long experiment, and then the potential changed, and you need to kind of like refresh the reference electrode, or have it sit back into its normal solution for a while to equilibrate before doing the next experiment, so it has a stable potential.
Yeah.
Um,
Mostly you're looking for that drift, right? I mean, there can
yeah.
be an offset,
Hmm.
which you'd potentially be concerned about because it would mean that the chemistry has changed or some other,
Yeah.
species is affecting the thermodynamics.
Hmm.
But to a certain extent, if your reference electrode is exhibiting a stable potential, it doesn't matter what it is as long as you
Yeah.
know what it is. It's
Hmm.
if it's drifting, that's the big problem. Because if it's moving, if you're
Hmm.
testing it against a stable reference couple and it's moving constantly or swimming around, going up or down over time, then you can't really know what your reference is in your real system. So you do need to use an internal standard like ferrocene. Some people add a bit of ferrocene if it doesn't interact with their redox
Hmm.
system for non-aqueous, right?
Yeah.
And you always adjust things to the ferrocene
Yeah.
E0 basically
Hmm.
after the fact, or you simply don't know. Frankly,
Yeah.
right? If it's moving around, your peak shows up at 400 millivolts. Who's to say on the next scan it shows up at 500 or 300?
Yeah.
Is that chemistry, right? Did your electrode get better on between cycles 3 and 4, or is your reference electrode just moving around?
Yeah.
It's hard to know the answer to that question, so you have to do some independent verification of your reference electrode, or
Yeah.
use an internal standard, like we said.
Yeah. Yeah. Okay. Juan Zapta. In a polarization test, what is the physical meaning of the multiple slope changes and subsequent current plateau observed in the anodic branch of a Tafel plot, particularly in corrosion applications?
It's a
Um,
passivation thing.
ah,
So I believe it has to do with there, and it's tricky because you want. I think typically for a Tafel for a corrosion Tafel thing. Where's my? There it is. Draw some stuff for you.
mhm.
No more zinc though.
Number six.
Okay. So when you look at polarization curve, you have potential here, and usually you have log of the current down here. You'll get something like the cathode. If this is like let's just say this is E core.
Mhm.
The cathodic one, you'll get usually something like that. And so, okay, great. You have your Tafel slope. The cathodic one's not usually as much of a pain. The anodic one, you'll get something like you described. You might get something like this, and then this. And there might be like two. I'm drawing it kind of badly and maybe exaggerated, but just so you see, there's two slopes. So this is the one that you would use to calculate your E core and I core, right? Where basically where those intersect. But then you might have this other slope right here. And it's because as you go further and further positive, you start a passivation layer. Usually it's on metal, steel, or something like that. It has to do with this process, basically, something like that. Exactly what it is, I'm not positive. Some sort of decomposition of the electrolyte or of the steel itself, or it's some it's always just described as a passivation layer, and I don't exactly know what it consists of, to be perfectly honest with you. But you start to get that formation on the surface, which is why this starts to go more vertical often, because you can just look at the axes. For example, the voltage is getting higher, but the current is not. Current staying roughly the same. I mean, it's log of current, but basically, as you increase the current, the voltage further and further, you're not getting more current out of it, which is like sort of it doesn't antithetical. You'd think that as you increase the over potential, you would get much more current out of it, but you reach a limit where you're just not anymore. Whether that's because of this passivation layer or because it's like diffusion. It's like it's the interplay between diffusion and kinetics. Like as you increase your over potential, your kinetics, right, in this part starts driving the reaction, right? And that's why you can do a Tafel transformation here, because it's kinetic information. So Butler-Volmer equation reorganization, but then as you increase it further, you're no longer really getting the impact of kinetics. So in some sense, this kind of double slope thing that you get because of passivation or diffusional effects is also a good indication that you should abandon the Tafel data at that point. You can point it out. People often note this. Oh, there's a multiple, I don't know, slopes or something like that you'll see in some Tafel data. But a lot of times it's like you're neglecting the purpose of the Tafel plot at that point fundamentally, which is that at that point in time, if it's no longer just kinetic information and you have diffusional or passivation phenomena, then it's the Tafel assumptions are broken down and you shouldn't even be doing Tafel analysis anymore. You can note this is occurring, but then say, okay, well, this is the slope that I care about, not this one, basically.
Okay.
Let's see. Where are we at?
Yeah, there are a lot of answers to questions after that. Lots of follow-ups.
Okay.
I think we're at Fred.
Yeah.
I think we're at Fred. Fred is saying, hello, folks. In EIS circuit fitting, why do people normally report the impedance in ohms per centimeter squared? Do I need to multiply the impedance with the surface area then?
So it's ohm times centimeter squared. Yeah. So the reason they do this is if you calculated impedance from current density instead of current. So impedance is analogous to Ohm's law. I've talked about this before, but you can think of the impedance, crossing my Z's, thank you, Chris, is basically I times, that's V, sorry.
Yeah, V equals IR.
V equals IR, so Z equals I over V. Right?
No,
other way around.
V
I'm
over
so
I,
good at this.
Which always confused me because I always like to be like, why?
V
like V over I
IR.
never feels right. But
I is V over I. Somehow I equated Z with V because I'm very good at science. Okay.
It's that cross and the Z.
That's right. It messed me up. The cross. See, if I didn't cross the Z, I would have had it right the first time. It's Chris's fault.
It's Chris's fault.
I blame Chris. Okay. So the reason for this is that when you have Ohm's law right here, V equals IR, the impedance expression is analogous. It's a similar situation. It's just that instead of resistance, we have Z, which is also a resistance, effectively, you can think of it. And so we have volts up here and we have amps down here. And a volt divided by an amp is equivalent to an ohm unit wise. And so all we have here is that if instead of amps, we have V over, let's just say J, right? If you use current density, then you have volts divided by amps per, let's just say centimeters squared. So the centimeter squared pops up because it's in the denominator of the denominator, right? And so that's equivalent to ohm times centimeter squared. That's it. That's where it comes from. So it's weird because it's like times. It's not like, it doesn't look like it's divided by. It's like, usually area normalized stuff, the area is in the denominator. It is. It's just that for this unit representation dimensionally, it ends up in the numerator. but it's still area normalized, so to speak. And the reason people do it is one of two things. It's either because, like I said, they just happen to use current density when they were calculating the impedance, and it just worked its way into the unit. And then the other is that it's meant to be a way to reproduce your data. I don't care for it personally, just my own personal preference. I find just seeing things in ohms is a little more instructive, because there's a lot of systems, and again, it's like, okay, well, if someone says they have 10 ohms centimeter squared or whatever, then okay, well, if I have a similar material I'm testing to this paper, but I have a different sized electrode, well, it allows me to multiply by my surface area at the end, or do impedance with surface area and compare with a paper. So that's nice. On the other hand, it's like, the very often, I would say, in impedance measurements and reporting of your data, people prefer to like things with ohms, like the solution resistance. Like, for example, in an aqueous system, the solution resistance is usually like 10 to 50 ohms or something. For non-aqueous, it's anywhere from 100 to 1,000 ohms. And it's like, that's ohms, not ohm centimeter squared. So if you start normalizing the unit, now it actually makes it a little more complicated if you're reading someone's paper to know, like, well, is that high or is it low? It's like, oh, they had like 1 ohm centimeter squared. It's like, oh, that's so low for an aqueous system, or whatever. Oh, well, they had a nanometer sized electrode, so that's why it went small. It's like, it makes you think a certain way about the values, at least in my mind anyway. I'm perhaps biased. I like to see things, and I know a lot of, I don't know, magnitude of units more, just sort of by rote, based on ohms, not ohm centimeters squared. So personally, I don't tend to look at it that way, but that's where it comes from and why some people use it.
I think like current density is useful when you're talking about like electrocatalysis and stuff like that, and determining like, oh, I got like a really great catalytic signal. Yeah, well, your electrode was super big. It's just normalizing to the area.
Exactly.
And I think it's just, I don't know if it's really necessary for these kinds of for impedance in particular, but who am I to judge?
Yash is following up here.
Yes,
the hydrogel should have a lower signal.
Baseline current signal. I was measuring for 1 to 2 minutes. I saw around 0.1 for solution.
So higher for the hydrogel.
Higher for the hydrogel.
It's actually backwards of what I think. Did we look at it right? I think
this is for a reduction reaction specifically. So hold on. Let me look back. The hydrogel signal was a lower negative lower negative current compared to the diffusion coefficient that was faster, sort of say. So so we had a lower negative current, and he is getting now, I mean, mind you, that was just changing the diffusion coefficient, because I thought, oh, if the electrochemical system is exactly the same, except you have a hydrogel versus like a regular electrolyte, then like that's just my initial guess as to what the values. So the hydrogel in this case has more current than for a regular solution. I'm trying to think. That seems.
I'm looking at a simulation again, just to sort of as well kind of compare here. So you're saying the hydrogel has a higher current? Is that what he's saying?
Yeah, he is measuring 0.3 microamps for the hydrogel and 0.1 microamps, for the solution. So he's getting a higher baseline current for the hydrogel than for.
There must be something else going on. There must be something in the hydrogel that's contributing to the current. Like somehow is the speed of the charging of the double layer slower, is the time constant longer, such that it has a higher current for a longer period of time? I know that's a diffusion coefficient thing, but that might be affecting
Yeah.
What's
So
the Cottrell equation? I mean, like, what I'm trying to
control equations. I'm working on I've been working on a chronoamp video that I'm hoping to get out within the
I'm just
next
trying
week
to
or
think it
two.
through. So, in addition to the diffusion coefficient, I mean, you might have
It's just time, area,
Faraday's
concentration,
constant.
and now that is for a purely diffusion controlled kinetics, you know, electron transfer species. Like that's it. So certain things that are important in chronoamperometry is like the initial spike in a chronoamperogram is partially double layer charging, but that's just going to be based on the time constant. 5 RC, 5 times the solution resistance, and the double layer capacitance is time. So like 1 ohm times 1 farad is 1 second. But when you have in traditional systems, when you have like microfarads or even 100 ohms of solution resistance, you're still able to charge this thing on like the micro to milliseconds time scale.
So if you think about it though, let's just use a crazy example, but let's just say that the resistance of the hydrogel is like really, really huge. Like it's a kilo ohm.
Okay.
So maybe the RC for the hydrogel is like way bigger, such that he's not even going 5 tau, and the current is just it's not charged yet. And so it's artificially higher, something like that.
So in principle, I'm going to say in principle, yes. But like, if you think about it, like, I think to a degree, yes, if you really want, if that hypothesis was correct, so like, okay, you go from 100 ohms to like 1,000 ohms or something. That's still just a 1 order of magnitude. You've changed something from like 1 millisecond to 10 milliseconds. And you're doing this experiment for 1 to 2 minutes. So like, unless the capacitance is also very large.
But what I said was even more. I'm just pretend it went from 1 to 1,000.
Okay, from 1 to okay, so 3 orders of magnitude.
Right. And and the capacitance, I mean, it's like still low. I mean, I don't know. I'm just pretend it went from like a second to 100 seconds.
Yeah. If it's a second to 100 seconds,
that seems egregious because usually a time constant for a double layer in solution is not that. It's way faster.
Yeah.
But let's just pretend.
Yeah.
That's one possible answer. The specifics might not work out in my favor here, but that's one possibility, that it appears over a short period of time because the time constant is larger. In other words, it takes longer to charge up the double layer in the hydrogel, that it has a higher current,
Yeah.
And then over the long run, it should have a lower baseline because of the slower diffusion. But in the immediate, so that's what's happening.
Here's another question, sort of say, is are hydrogels, because as you said, like the resistance can increase. So usually I am curious about the consistency of a hydrogel from like how conductive it is, because this is another one of those weird things in electrochemistry where if the conductivity changes, it has a twofold effect. Like if you change the concentration of the supporting electrolyte, the effect is twofold. It changes both resistance and capacitance simultaneously. Like it's not one or the other. So you think like, oh, if I have my like RCT, oh, maybe, or sorry, my R times C, oh, I just want to change the resistance. Well, your capacitance is also going to change too. Or if I just want to change the capacitance, your solution resistance is also going to change. Like both of those things happen.
So let me show you something I'm doing with simulation here, just to illustrate this point, because I think this might kind of help cement that home as well. Okay. What I've done is I did the same simulation Alex just did, basically, right? I did current. Yeah. I did this is like a bulk electrolysis with 1 E-5 diffusion coefficient, like standard stuff. I did an oxidation, so it'd be positive. It's just easier to see, in my opinion. But anyway, it's the same thing. Alex just showed it negative. I'm showing it positive. It's a decay curve. The exact values are irrelevant. I think I picked like 200 millivolt over potential, 60 seconds. Great. There's my decay. Now, for example, instead of changing the diffusion coefficient, what I've done is gone in here. As part of our software, you can adjust the double layer capacitance and the resistance. This is the time constant, basically. So what I did is I just added some uncompensated resistance. Let's just say 500 this is a hydrogel. It's a more resistive, right? And I added a little. I just picked it out. This is what is this, like 100 microfarads? I don't know. I just picked some small number. Let me simulate this.
Mm-hmm.
Okay, so I've added capacitance because before these were zero. It was not taking into account double layer capacitance or anything. Now let's zoom in and see. So the faint red line is before with basically no time constant. Like it's zero. It decays immediately. Well, look here, same diffusion. Now I could adjust the diffusion coefficient too, because that might be occurring. But basically, look, this is, for example, hydrogel. This has a higher resistance than before and maybe a higher capacitance. Well, look at that. It's a higher baseline.
Mm-hmm.
And it's just because of the difference in the decay of the time constant that at any particular time, I'm at 5 tau right here on the first one, like immediately.
Mm-hmm.
But here I'm only at like 1 tau, and then I'm at 2 tau. And by the time I hit 4 or 5 tau, I'm at 90 tau with the other one, because like the time constant difference, it's just a difference in how quickly they are charging up, I guess. So something like that.
Yeah.
I don't know if that is a satisfying explanation, but it seems to fit from playing with these parameters here. I can increase this further and you see it starts to the difference gets even more stark. But
it's
so anyway, I mean, just after a while, you see that there's just a pretty consistent offset that's just going to persist. They both are decaying. They both are getting smaller by virtue of the Cottrell equation or whatever. But there will always be a difference in them because they're decaying. One of them decayed faster initially, something like that. So I don't know. Maybe that's an answer.
Yeah, maybe.
So.
Have to play around with it a little bit more.
I think the tricky thing about that is that in the context of the Cottrell equation, it doesn't take into account that part.
No, it doesn't.
So our simulation software is, but the Cottrell equation directly doesn't. So
yeah. So usually you want to when you're doing any experiments with the Cottrell equation, you want to like omit the first several data points because they contain 5 RC worth of charging, and then you keep. And then you take the points after that. But then you want to be careful. So even 1 to 2 minutes, 1 to 2 minutes is probably fine. You want to be careful about convection. So if you just have a solution that's just kind of standing there, you'll get some subtle vibrations, which can change the current. And then that's also non-Cottrell. So that's another thing to kind of keep in mind as well.
Yeah.
Okay. Let's see. Let's continue. So looks like an NVS Praneeth is saying, can you make a small tutorial on open circuit voltage decay and Mach-Schottky analysis in a photoelectrochemical system?
It's not specific enough.
Yeah.
I'm just kidding. I am actually working on a webinar of Mach-Schottky. It will probably be done in 8 years. No, I'm trying to get it out, and I have a lot of other stuff. And anyway, to that answer, I'll tell you that at some point, hopefully in the next, I don't know, 6 to 12 months, I will hopefully be giving a Mach-Schottky webinar. I've been trying to put one together. I've mentioned it before, and it just takes a long time. And I have a lot of other high priority things I have to do in my job, unfortunately, that don't involve webinars.
Yeah.
So it's been in the works for a while. Anyway,
stay tuned for the next 6 to 12 months.
Exactly. Just wait by your computer.
Yeah.
Refresh your email constantly, and eventually you will get an email that I am doing a webinar on.
But if you don't have the time to wait around for 6 to 12 months, because I mean it's not that long, but some people are impatient. You can always subscribe to our YouTube channel and just click the notification icon, and then you'll get a notification when one of these things comes up. So
yes, that too.
Subtle
right.
Subscribe. Doesn't right. Then you can do other things, and then your phone will tell you.
Yeah. Hey,
when
Alex,
it's ready.
Is there a YouTube channel that does a good job with this kind of thing?
Yeah.
Funny enough, you should say there is.
There is.
Very, very subtle.
Very subtle.
I don't think they caught on.
All right. Let's see. Oh, Chris has to go to platinum right now.
Yeah, he always goes to platinum at this time.
Yeah, he goes to platinum at this time. Thanks for stopping by, Chris. Always good to see you. I hope the platinum is doing well.
Thanks for the Z. crossing advice
C
that made the whole live stream.
Yeah.
It made the whole thing. That's right.
All right. So let's see. So actually, Morfolino is just, I think, commenting on. I think he's also talking about the hydrogel situation, which we've already discussed and stuff. So doesn't look like there are any questions.
I think we've
got all the questions. Nothing also in LinkedIn, which is okay. You know, we're trying to stream to new platforms where people are. I know a lot of people. I think a lot of you guys may have actually reached out to me on LinkedIn. So I'm like, okay, let's also try to do these live streams as well to LinkedIn and have other content on LinkedIn, because they have there's a big audience there too.
And I think also to a good degree, the at least from what I can tell, the LinkedIn live stream sort of is it newer? Like I don't know that it's as fleshed out as YouTube is like a video platform, obviously. So YouTube's got this stuff pretty well down.
I think LinkedIn
I think it's pretty
is newer. Definitely. But
so I'm sure the proliferation of events on LinkedIn will maybe grow over time, but it's not quite as common, I suppose. At the moment, but we're going to keep streaming there because
you're happy
to reach new people on all the different platforms. We know that a lot of you find us in different ways, and we want to be available in as many of them as we can.
Yeah. Looks like we just got a new question.
Yeah, Umar is asking something about lithium here.
Yeah, your favorite.
That's my favorite. It's not as cool as the Nernst equation, but I do like lithium. Can you please elaborate on how to find lithium plus redox potential using OCP or RRDE? So OCP isn't really going to help you. If you're talking about, like, I've got a material for an anode or a cathode and I want to find its potential, RRDE isn't exactly you can basically, it's one of the few instances where cyclic voltammetry is used in battery research. So you would do something like set up a very small 3 electrode system with your active material, or you'd construct a coin cell. In fact, actually, that's a lot of times this is a better way to do it. So, like, if you're studying an anode material and you want to find its redox potentials, where it intercalates or alloys or converts lithium, for charging and discharging, or a cathode, either way, you would construct a battery or a cell with lithium metal as the other electrode. Whether you're doing cathode material, lithium metal as the anode. If you're doing an anode material, lithium metal as the cathode. And so what it's sort of doing is using lithium as both the reference, hence using Li plus as the actual reference, in addition to the counter electrode of your material that you're studying, right? So that it means that it has an infinite source of lithium, basically. And so either an anode or a cathode, depending on whether you're charging or discharging, involves a process where it is bringing in or releasing lithium ions. Okay. And so if you have a lithium metal as the other electrode, it's like a perfect source of or deposit location for lithium ions to be, put into as lithium metal or removed from. And so you simply do cyclic voltammetry very, very slowly. I'm talking like 100 microvolts per second, so like 0.1 millivolt per second scan rates, like really, really slow, over a wide potential window, and you look for where the peaks are. It's very, very similar to CV of anything. It's just that you're always going to scan very, very slowly, because otherwise it's equivalent to very rapid charge discharge, and you won't it's a bad idea to do that to a battery, basically. And so you'll find the redox peaks, basically. A lot of times you'll scan no more than 2 to 4 or 5 times at most, because usually the first scan involves things like the SEI formation. And so your first like CV will be different than the subsequent ones. You'll usually have a big like reductive peak that corresponds with the SEI formation. It won't appear in the next CVs. And then you have peaks, and those are the peaks of the process under study, right? And that's how you can find the redox. And then, when you're using the material, roughly what potential or voltage its process of interest is occurring at. And that way you can calculate cell voltage, you can calculate, how well your battery is performing, basically, right? And do charge discharge kinds of experiments and things like that. So that is sort of the most common thing. In a lot of battery papers, you'll see like it's a typical kind of I don't know, order of operations with the like results section. You'll see all the materials characterization, and they make their thing, and then there'll be like the first electrochemical test is usually CV that just shows this is the the voltammogram of the native species or the raw species, or what this is how it works. And then it's the charge discharge, but you'll show the CV to kind of show the lithium plus redox processes and where they occur, sort of as it's just like background information, whatever you want to call it. So that's what I would suggest. Yeah.
All right. Very, very good. I guess I was thinking about the lithium plus lithium redox pair as like just any other, redox couple, and you can use all the usual techniques, but maybe lithium plus is different.
It's not that it is different in some sense, because it involves usually really high potential. It's like minus 3 volts or something versus like SHE or whatever. And just because of the nature of batteries, it's like you have to do CV really slowly. So you wouldn't really do like a scan rate study. In theory you could, but it's not wise for batteries.
Yeah.
Largely because of this time constant thing we talked about. It's like the capacitance of a battery is huge. It's like 6 orders of magnitude higher than like a glassy carbon in a.
Oh wow.
When you're talking about if you get the like capacitance, like the double layer capacitance, for instance, of you probably we've done do EIS on like a glassy carbon disc electrode in sulfuric acid. It's like I don't know, it's like 10 microfarads or something.
Yeah.
So, in that range, maybe it's nanofarads.
Yeah.
I don't even know.
Yeah.
The capacitance of a battery can be a farad.
Oh wow.
Or like millifarads at minimum. Depends on how big the battery is, obviously, right? But you're talking at least 3 to 7 orders of magnitude greater.
Wow.
So why do you think it takes an hour, 2 hours to charge up a battery? You can charge them faster, but like generally it takes like minutes to charge a battery because its time constant's enormous.
Interesting.
Right? Like technically speaking, you could think of it that way. It's like in some way that's a reason. There's other stuff going on, but like that's one way to think about it. Basically, it's like the R times C is bigger because C is massively huge. So its capacitance is so big. If you polarize it so fast, you end up with a lot of I think that the impedance gets like really large because it can't charge up the capacitor fast enough. It's something like that. Something like that. It causes all kinds of problems. In addition to just other stuff, like you'll damage the battery. It's just one of those things. It's like with electric cars. It's like, can we charge up a electric car in 8 minutes or 4 minutes? It's how long it takes to fill your gas tank, right? That's the main like one
of the big drawbacks.
Well, it's just one of the main like points of comparison when you compare like in the future, if we are able to get to a place where we've replaced the bulk of petrol or diesel powered vehicles with electric vehicles. For people living in cities, we already have that answer. Like you can buy a Tesla and you can charge it at your house. and you can drive to work every day. And as long as you're driving fewer than 300 miles or whatever the range is, it's in that range. It's like 200-300 miles, whatever. Yeah, you're fine. Like you can charge it at night or whatever. You can even drive multiple times because you could drive. Do you have a 10-mile or 20-kilometer commute? You could drive multiple times on one charge. But you have time. But it's like if you're driving a lot more, or you have you live in a more remote area, and you need to, like right now you can drive almost anywhere in the world, literally almost any country in the world, and you can find a gas station and fill up your car, right? And it takes you a few minutes. So that's the challenge on a massive scale, to have electric, in addition to a bunch of other things, right? But like generally speaking, the fast charging is the thing. It's hard. It's hard to charge up a battery that quickly and have it perform, not explode, and perform over any appreciable amount of time that someone would own a consumer electronic. Because even now, like our phones, I talk about this from time to time, but if you charge your phone up and you get the charger for your iPhone or your Android phone, and the chargers now are typically things like I don't know, 2 amps, 3 amps. They're high, the USB-C and the plugs that we get now. I think it's similar in a lot of other countries, at least in America, we get things like that. It's more current, so it charges faster, And what they're banking on is that people will get bored of their phone before the battery dies. Which is mostly true. People like to get the new phone every year, so they don't care that they're destroying the lifetime of their battery pretty quickly by charging it up in 40 minutes or whatever. Right. It's like, you shouldn't charge a battery that fast. It's not going to last that long. And I'm someone who hates getting a new phone, and I'm someone who knows how batteries work. So I don't use fast chargers. I have like old chargers that only give, less current, and you can limit your battery to 80%. There's ways you can kind of extend the longevity of your phone battery. Because I hate getting new phones because I'm old and cranky. And I don't like learning new things.
No, but that's well, I mean, and that's an interesting thing, like, because that, but also the tools we have, like if you had it your way, it's like at night you charge it at like the slowest rate possible, so that when you wake up,
if I could, I would charge it at like C/8.
Well, is it C?
Sorry, it'll take 8 hours to charge.
Take 8 hours to charge.
Okay, or whatever long, if I get 8 hours of sleep, which is always the thing. Just whatever. Like like I can't charge it that slowly. I mean, I could probably make something, but I'm not going to do that. So it would be a bad idea. Like if you start messing with that, you might accidentally overcharge. Like you'd have to.
That's
like
true.
the chargers you buy have like some sort of system that
prevents them from like overcharging and stuff like
essentially
that.
And you want to make sure it would turn off, because if it doesn't, you're screwed.
Anyway. That's a good
I don't recommend necessarily homemade chargers stuff unless you really know what you're doing, and I don't. So, I know electrochemistry, but I don't necessarily know like electronics.
That's a very interesting.
There is a difference.
Right? Although I've been changing my because I continue to learn more and more like electrochemistry as time goes on. But I've kind of been changing my view or definition of electrochemistry. Like many people will describe it as the combination of chemistry and electricity. But I think it's more so the combination of chemistry and electronics. Because even things like charge transfer, like we think about electron transfer, I'm like, electrochemistry is not always about electron transfer. And more often than not, you're thinking about these more like you're always hooking up your electrochemical system to like a battery, a power source, but more often a potentiostat, which is a much more complex electronic piece of equipment. And the potentiostat settings and the electrochemical system, they affect each other, and it's going to change the kind of results you get. So,
well, a potentiostat is just a big box of resistors.
It is, right. A big box of resistors and capacitors.
It's a big op amps. It's a big expensive box of resistors.
Yes. Yeah.
I love saying that because it trivializes everything that my company does.
Yeah. Well, that's funny.
It's not entirely false.
Not entirely false.
It's a little more complicated.
There's definitely a lot of
electronics.
Well, I guess when you think about all electronics, like even like how like the railroad, like subway station things, it's like it's just a bunch of like
Plus electronics.
op amps and diodes and converters, and just throw a bunch of this stuff together. It's like, I don't know.
What's an airplane? It's just a bunch of electronics.
Yeah, and like
stuff
and some
as-
big pieces of sheet metal
as
with
you're
wings.
hurtling through the sky at 50,000 kilometers at 900 kilometers an
It's
hour.
just a giant steel tube.
Giant
That's
steel
all
tube.
it is.
Yeah, whatever. It's just a big steel tube hurtling through the air. You know what's really funny?
Yeah.
Just add this anecdote.
Uh-huh.
Have you gotten to the point now where you travel? Like I've gotten to this point, and it's like it feels like psychologically it makes no sense, but it's when you're in a
Mhm.
plane and it's a really big plane, you feel safer. And if you're in a small prop plane or something like that, it feels like it's gonna fall out of the sky.
Yeah.
It's like, why do I feel safer in the larger, more massive, heavier metal tube
Yeah.
soaring through the sky than a smaller one that's more lightweight,
Well, I think the reason why, because
mean-
I have the same thing. Well, this is real talk. Whenever there's like some kind of like storm or hurricane system,
Yeah, it
the
affects-
big international planes
Yeah, they're
that are
safe.
gigantic, they're like
doesn't matter.
wind. That doesn't matter. They
Yeah.
still go up.
That's true. It can mess with
They can-
smaller.
They can
aircraft.
just like overcome
guess.
all those things.
It's just like it's just sort of like fundamentally, you
yeah.
would think like psychologically,
Yeah.
we would be more freaked out by like, oh well, there's this small thing, like we can get this off the ground and fly, like
Yeah.
just okay, it's less massive. I understand about lift,
Yeah.
whatever. Like it shouldn't be that hard to get it off the ground. Maybe okay, maneuvering it's gonna be hard if there's a storm, I'm in trouble. But like just in
Yeah.
general,
Mhm.
when there's a little prop plane or whatever, and it's like, oh my gosh, this feels like this is gonna fall out of the sky.
Yeah.
But this giant thing that probably takes like 90,000 times more energy to keep in the sky
Yeah.
for a 1 second. That's way better.
Yeah, that's right.
I feel so much
I feel
safer.
Much better.
If this thing were the size of a planet, I would feel so much safer. Like,
Th-
it's
okay.
weird.
This is the real reason you feel safe. On those little prop planes, it's like, you're just going there, you're just going from point A to point B. But when you're on the giant planes, man, they actually serve you some food and drinks. This has to be safe.
Yeah.
Like they're giving me dinner
That's
or
right.
lunch.
It can't be unsafe
It
if you
can't
can
be
go
unsafe.
upstairs in the plane.
Yeah, that's right.
You can go upstairs in the plane and like sit at the bar and have a margarita. That's definitely safe.
It's definitely
They're
safe.
not just liquoring me up as something terrible might happen. That's totally not what's happening. That's funny how much we've taken. Like,
yeah.
Sometimes you think about it too. Just I'm sorry, I'm rambling. This is just kind of fun.
This is also
conversation.
to say that we travel, so you should come visit us
Yes,
when we're at different
do.
shows and things like that.
But that's the thing about traveling too, is you start to realize like how much do we take for granted that like we can get in an airplane. We're on the East Coast of the United States.
Yeah.
We can get an airplane and be in Europe in like 6 hours.
Yes, which one of our colleagues is about to do.
That's true.
True.
But it used to take like 9 months in a wooden ship, and 80% of the people would die of scurvy on the way. Like,
Yeah.
that's how you used to get across the Atlantic Ocean. Now we just sort of like, oh, there's not even Wi-Fi on this flight.
I know.
You
That's
know?
right.
Like, you don't get to complain about that. You get to go by morning and be in France, like, or
Yes.
England. Like, you don't
Yeah.
get to complain. You just don't. You're not allowed. I don't care if they strap you to the propeller. You're not allowed to complain.
You
know?
can watch 100 movies in one of these planes. Like before, people just
Die.
sat there. Well, they would just, even on a plane, they would just sit and
That's
do
right.
nothing. They also dressed up.
Yeah, people
People
dress
used
up.
to dress up.
Well, you
for
want to
food.
make the plane impressed, so it takes you where it's going.
Yeah.
If
yeah.
the plane doesn't like the way you look, it spits you out in the middle of the ocean.
Yeah.
And you have to
yeah.
swim the rest of the way.
It reluctantly,
That's right.
takes you in.
This is science.
This is science.
Yes.
Okay.
And with that-
with that, thank you for another. I'm glad Chris went to PT, because then he would say, you know what you guys really need? An outro, which
That's
is another.
right. We don't have an outro.
I
We
need
do
to
have
work
a
on an outro.
fancy new intro. And we
Yes.
hope that you'll join us next week. You don't even have to ask any questions, but you could just see the intro.
Yeah,
'cause
you
it's
can see the
brilliant.
intro. You should stick by to see the intro, because then
That's true.
you can start typing your questions in, and we can answer them.
That's right. But thank you all very much.
Yeah.
We do keep things lighthearted here. And anyway, we do appreciate the questions. We hope everybody had a good time. I hope this was useful. If you have a question afterwards, please leave it in the comments. We will answer it later or in the next episode. And we look forward to seeing everybody, I guess, next week.
Yeah.
And
Yeah.
have a good weekend, everybody. Take care.
Take care.